Our last speaker for the session is Carey Priebe, who will be speaking on repeated motif hierarchical stochastic block.
Thanks, Dave. So it's been a great week, but I feel a little bit like that kid. Nope, it didn't work, Carl.
No?
Well, we'll see what happens. You might not be able to see the pictures because
Projector.
you can't see that picture. I'm trying to use Carl's computer, so no thanks, Carl, for letting me use your computer. So who knows what happens here. It's kind of a bad place for that to happen because the outline for my talk is to describe this picture. But I can draw it on the... While Carl sabotages my career, such as it is, I'd like to say that the outline for the talk then is to describe that picture, and I want to start with I want to say what the picture is, why I care, and how it works. Yeah, it's lucky that I already have tenure, but I think they can revoke it probably. Not for bad talks, thank goodness. So how it works is largely described in this paper by Lazinski et al. About the hierarchical stochastic block models and then the changes required to make it work for this particular today's talk. What it is going to take a while to say, but I want to start with why I care, and why I care is really described well in this paper, a 2014 science paper by Marcus, Marblestone, and Dean. Really why I care is this problem was given to me as a challenge problem by neuroscientists, the Vogelstein brothers, in 2013, so 3 years ago. They gave me a neuroscience challenge problem describing things in neuroscientific terminology, and I think I've turned it into a statistics problem, one that I can't solve, but I've turned it into a statistics problem. And it's also very related to Misha Chklovsky's neuroscience grand challenge that he described yesterday, which was to identify computational primitives. So from the Marcus, Marblestone, and Dean perspective, here's the motivation. This is why I care about today's talk, other than I like to hear myself talk. So the paper is called The Atoms of Neural Computation, and this is actually from the Frequently Asked Questions forum. The first thing is that one common view holds that the human neocortex consists of a single, massively repeated canonical computation. So in my notation, that's going to be M is 1. So we have capital R things, subgraphs, and capital M is how many distinct ones are there, because we have this repeated motif idea. And the one common view apparently is that capital M is 1. It's all from 1. And then MMD say an alternative suggested in this science paper is that the cortex consists of a diverse set of computational distinct building blocks. And so that's capital M is greater than 1. It might equal R, in which case every building block is distinct, but it probably doesn't equal 1 or capital R. It's someplace in between. There's some repeated motifs, but you have more than one of these Micha's computational primitives. So that's the, I'm going to define it in terms of, or try to define something mathematically that would be the cortical column conjecture, but this is what the neuroscientists might say about it. So here's a little bit of a story. In many disciplines, we think that a big graph is composed of loosely connected smaller graph primitives. So the idea here, well, on the left I have a hierarchical stochastic block model, which I haven't defined, but the idea is that there are 8, along the diagonal here, there are 8 stochastic block models. Each of those are 3-block stochastic block models, and hidden inside the big graph is 8 of them. And then the colors here indicate a motif equivalence that I'll define in a moment. So there's 3 motifs. There's 8 of these loosely connected smaller graph primitives, and each of the loosely connected smaller graph primitives has itself some substructure, here described as the sub-stochastic block model. So this green stochastic block model and that green stochastic block model are the same model. So the idea is that the cortical graph has a whole bunch of these loosely connected smaller graph primitives, capital R of them. Each one looks like this. It has n sub r vertices in the induced subgraph. There is internal structure there to give rise to whatever this thing computes. And then the question is, how many motifs, how many distinct versions of this internal structure might we have? M equals 1, M equals R, or someplace in between. Okay, so the one version of the cortical column conjecture is using this picture. I have two models that I haven't described yet, and I observe a graph. And if I could set up these two models so that M1 in this first model, where's one? Yeah, in this first model, it has capital M1 equals capital R. That is, there are no repeated motifs. There are capital R of these loosely connected graph primitives, but they're all distinct, versus M2 in the second model, M2 is strictly less than R. So that would say repeated motifs. So if I could decide which of these two models best fits my observed graph, I could address the cortical column conjecture. So this is, I'm not going to describe too much about this, but this is from this paper, and these are the smart people. And just for what it's worth, I think you can find code and simulation and even real data at that page for what it's worth. So we want to start with a random dot product graph. I want to start with a latent position model because that's what I do. That's what I like to do. So we have a distribution capital F on a subset of RD such that the inner products can be interpreted as probabilities. And we say that a graph A and its unobserved latent positions X is a random dot product graph under distribution capital F. If I have the n latent positions, IIDF, and we have our standard latent position model, conditional independence. And we know that a stochastic block model, get rid of Harry's circle and draw a square. We know that a stochastic block model can be interpreted as a latent position model. So in this particular case, if that's script X, and I have capital F is a mixture of point masses. Well, now that Trump's in charge, we can do anything we want. And you have to do it too. So the idea here is that I have this stochastic block model, but I want to think about it in terms of the latent position model. I'm doing a random dot product latent position instead of something else just because, let's be honest, for mathematical expediency. So that everything works very nicely for the random dot product graph and a little bit less nicely for the Laplacian, but we can make it work. And so the hierarchical stochastic block model is just that same thing, except each of the, so there's capital R of these groups, and each of the groups, for simplicity, for notational simplicity, and even for me for conceptual simplicity, I'm going to say that each of the R primitives are K block models instead of an index on K, but we certainly could do that. And so the idea is that each of them is itself a block model. So if I think of those as the latent positions for one of the capital R primitives, now there's 3 in for that one, so that the 3 point masses here and the 3 point masses there give rise to the substructure, the internal structure of these graph primitives. And so we can define that, and then of course it turtles all the way down, so we can go another level, but it hurts my head. So once we're there, we can define what I mean by motifs, and these are not Sophia's motifs, they're not computer scientist motifs. First of all, well, the definition is if I have two random dot product graphs, A and B, with distributions, importantly, F and G, we say they have the same motif if there's a unitary transformation so that F equals GU. And that's because of the identifiability. Any rotation is the same stochastic block model. So essentially that says we have the same distribution for this subgraph, this induced subgraph. Notice that it's only a motif stochastically. So I certainly don't think it's exactly, we're not looking for a particular subgraph count or anything like that. But that's fine because, in fact, we definitely want that because we don't believe that the synapses between neurons, I mean, there's stochasticity in there. We don't think that even if we had this computational primitive, when I say we don't think so. First of all, I don't want it to be true, and Meech is in the audience, and who knows what the neuroscientists think. But presumably, it's not an exact copy. It's just, for us, a stochastic copy. And the other thing is that these motifs are quite a bit bigger. So I don't know how much bigger. Meech's talk, he was looking at this thing that calculated the PCA or whatever it was, and I don't know how many neurons it was going to take in the end, but the Vogelstein brothers suggested to me that they'd be on the order of 100 neurons. So we're thinking about each of these subgraphs as having 100 neurons, and then they have some substructure within those 100 neurons. So we're talking stochastic motifs and bigger than 5 or 10 vertices. But the substructure is the key. Okay, so then to understand, so that's why I care about this problem. I want to formulate models so that I can do some sort of model selection so I can address the cortical column conjecture because there's no Nobel Prize in statistics. And I'm older than 40, so. Which is probably not the only reason I won't win the Fields Medal, or even the main reason. So now I want to talk about what these two models are. So I'm going to consider these repeated motif hierarchical stochastic block models, two different ones. And so we ought to describe that, and so you can read that while I wait. So what we're trying to do is formulate models so that we can subsequently formulate a model selection procedure for deciding whether a hierarchical stochastic block model graph supports the conjecture of repeated motifs. So if we start with the collection of graphons, just the standard thing, then the first thing we do is we define script fk, which is the k-step function graphons, also known as stochastic block models, basically. And I want to point out here that, so there, as Harry suggested, you have about k squared parameters there. Okay, but I have that, and so when I defined motif a moment ago, I intentionally lied, but I forgot to say that I was lying when I said it. We want to do something even more. So the stochastic block model given by those 3 points in script x depends on the location of those points and also the mass of each of those 3 points. Those are the pi's, or the block probability membership vector. And we want our motifs defined modding out by that pi. So we're going to define this pi equivalence, meaning if we were writing it in standard stochastic block model notation, they have the same B matrices, but we don't care whether they have the same pi's or not. So we're going to look in this quotient space. But anyway, we start with a stochastic block model on k blocks. Now we extend it to multiple graphs, so we get our hierarchical stochastic block model, which we index by r comma k. And it's just a rk stochastic block model, r times k stochastic block model, but we've defined it so that only so that there's a bunch of blocks that don't matter. They have small interconnectivity probability. The guiding principle was that the graph consists of a collection of primitives loosely connected. So since they're loosely connected, I don't much care about these off-block diagonal probabilities. And because of that, that's the only reason there's a hierarchical stochastic block model, because it's just itself an RK block model, but I can reduce the parameters enormously by only caring about the RK squared instead of the RK squared, if this is on video only. Okay, so there's my multiple subgraphs, and then the repeated structure is just saying, well, there's a collection of capital M, let's say, of these B matrices, B bar matrices, and all of the B matrices, or equivalently, all of the locations for the latent positions associated with the individual primitives have a configuration to give the same connectivity probabilities. There's only capital M of them instead of R of them. And note again, I'll repeat, that we don't care about the probability, the block membership probabilities, but only the block connectivity probabilities. And so that then gives rise to script F R M K, the repeated motif hierarchical stochastic block model, and MK squared, if M is small, compared to R, is smaller yet. So we're saving parameters, and that's in some sense the point of doing it this way. And we also define motif equivalent, so really, let's see what the next slide is. Nope. In the figure, I have the blue, maybe a blue model and a pink model, and they're really quotient spaces botting out by this motif equivalence. Okay, so now, given that, the question of whether or not I have repeated structure, I will address by saying, well, let's fix capital R, and given M less than R, how well G is best fit by an element of FRRK, that is, there's no repeats, versus how well it's best fit by RMK prime. And so M less, if the answer is the second, then I have repeated motifs. M equals 1 versus M greater than 1. I'm doing M equals R versus M less than R for kicks. Okay, so M equals 1 is a single massively repeated canonical computation, and M greater than 1 is a diverse set of computational building blocks. Okay, so now that I have those two models, I understand what's giving rise to the graph that I observe. If I can find the orthogonal projection onto each of these two models, I'll ask which of them is bigger, and I will do my model selection that way. And here's where we go from a conference where a bunch of people talk to a workshop where they say things about what they can't do. So if we choose M1, M2 are K2 greater than K1, so that the model parameter spaces are of the same dimensionality, now it's an easy problem, and I don't need to be smarter than I am in order to do some stuff. So the idea is, since this one has R subgraphs, but only M2 distinct motifs, I can have more structure in each of the distinct motifs and still have exactly the same number of parameters of this. So K2 is allowed to be bigger than K1. So another way of talking about this in model formulation is that if I'm willing to assume or live with this idea of repeated motifs, even just clustering my clusters and deciding that some of them are close enough that I can model them with fewer parameters, then I can afford to have more structure within each of those blocks. So if I set it up so that I have that, then, and if I can get the right p-hats, if I can get really good p-hats, L2 projections, or better yet, MLEs, then T greater than 1 provides evidence in favor of the hypothesis that the graph possesses this repeated motif structure. So I can answer the question for the simpler case. So now, how do we go about doing that? Well, there's an algorithm, and it uses spectral clustering, and then more spectral clustering. But instead of that, which you can see in the paper, we'll have that. So I have my graph. I do spectral cluster, or I do spectral embedding, I should say. And the thing to note about this, first, the spectral embedding is much easier. So when should you believe in stochastic block models or hierarchical stochastic block models? Never, but all models are wrong. This one might be useful. But how do you do model selection? Well, in this particular case, the don't need that. The scree plot for this overall graph, I mean, if it were really nice, would have an elbow at capital R and then another one at RK, because it's really an RK block. But this one's going to be easy to find if, in fact, they are loosely connected graph primitives. So first we embed into the wrong dimension, and in the wrong dimension, that's why this didn't erase, because I needed it. And in the wrong dimension, I can't draw this because I'm not in high enough dimensions, but in the wrong dimension, each of these guys, since these are more tightly connected within than between, each of these guys is kind of going to be on its own canonical axis, say, and so it'll be easy to cluster into the capital R groups. Once I cluster into the capital R groups, I go back to the induced subgraph in the original graph. I re-embed, but now the conditional scree, so that's the scree plot, the conditional scree just has a elbow at K. It's a much easier model selection problem as well, if we're doing some sort of singular value thresholding. So there I get my individual model estimate for the individual primitive. And so then that gives me, now I'm only caring about the, if you will, the block connectivity matrix. And so that gives me p hat 1 when capital M equals capital R. And the argument in the paper, in the original paper, can be extended to say that this is at least trying really hard to be an L2 projection onto that model, that quotient space model that I described above. And then, given this, I can take these individual identified groups and I can ask how similar are they. I can cluster them into capital M clusters, and now I have the projection onto script F2. So I get my two projections, p hat 1 and p hat 2, which is all that I need in order to calculate my test statistic. So again, this is the case we talked about before. There's a little bit of gray off diagonal, but those probabilities are small. The paper gives an upper bound for how big they can be before this works, you know, before we get some sort of consistency. And so we find, when we do this, we find eight subgraphs, and we just keep dropping this probability until we do, so we can make the picture. And then when we take those 8 subgraphs and we do that second step, we cluster them into 3 motifs, we get, this is a heat map of the cluster, of the similarity, a heat map of the similarity, and we see that numbers 5 and 7, which are the 2 red ones, cluster together, so we get the right 3 clusters. So R hat equals 8, M hat equals 3. We've estimated the right values for R and M. Wonder what the next picture is. So it's definitely the case that if I knew R and M and K, and I had a projection that I could do that model selection, if I matched the parameter dimensions, then t greater than or less than 1 is the right thing to do. I do not know how to do the test when I have to estimate M and R. I mean, I know how to do it, I can't prove that it works, of course. So here's the simulation results. This is our test statistic T. These are box plots for the test statistic T under 2 cases. The first case is when M is R. Remember, T greater than 1 is evidence in favor of repeated motif, and T is less than 1. And the distribution, in fact, of this T is what you'd expect, but the box plot. So for this particular pair of models, it always works. 1 is the right thing. So what I don't know how to do is among the many things I don't know how to do. What I'd like to come up with is a way to pick that eraser up without having to bend down. But barring that, what I'd really like to do is look at A minus P hat in the model 1 plus, so the fit plus some sort of penalty, which is presumably going to be a function of, well, that's a good question, right? Exactly how this is going to work. It's going to be a function of D, which is the dimensionality of the parameter space. Not all parameters are created equal, but they're equal enough for this kind of purpose. And presumably N and M from the observed matrix. And I'd like to know how this penalty term should behave so that I can choose amongst models, so I can do a proper model selection. And then if I could, then that would be another way to estimate M, R, and K for that matter. Okay, so I didn't have this in here, but this is, in fact, Mieczykowski's fly data from the 2013 Science or Nature paper that he described yesterday or the day before. Everything runs together. Where he found, he calculated, no, he traced the edges amongst neurons in the Drosophila brain. Okay, so this is Miecz's data. We've had it for a while. In this particular case, there's like 1,500 neurons here. He showed a little schematic with a much smaller number that he had fully, I believe that was the graph that you fully reconstructed. But anyway, if we take this graph, and now I've already ordered it so that it has some structure, but if we take this graph, and it's a directed graph, and if we do the first step, we come up with 8 clusters. R hat is 8. So we find evidence in favor of 8 loosely connected graph primitives. And then if we do the clustering of those 8, we get this picture. Again, cluster similarity is given by this. And in particular, then I throw the dendrogram up here. The clustering is not dendrogram clustering. But in particular, these two regions are very similar to each other and different than the others, at least according to a cluster. It's not quite a BIC, but average silhouette width model selection also says I want M hat equals 2. So the idea here is that there are, the first guess, R hat equals 8 of these loosely connected primitives, and M hat equals 2 clusters of them. And then we also have information from Mitya about the individual neurons, and the 2 that were clustered together were 2 layers or 2 columns that were close to each other. It made sense to Mitya at the time. Okay? But I want to emphasize that coming up with an estimate of M, that is, I think that there's 2 clusters here if I was going to look at the dendrogram or any clustering analysis on these stochastic block models. So there's 2 kinds of clustering going, right? I cluster the neurons, or the vertices, that we hear so much about, and then once I get individual primitives, I cluster them, so I'm clustering graphs themselves, a collection of 8 graphs, and I cluster them into 2 clusters. But that's M hat equals 2, and believing M equals 2 more than M equals R are different things, okay? So I can't quite, the idea that if I were going to cluster it, I might want to cluster it into 2 is a little bit soft, I'm afraid. Okay, so Da Zheng, the great Da Zheng, is a PhD student. When I got here Sunday, he's now a doctor. He defended on Skype this week. And he's my computer science genius, and he's got this flash graph, and now he's got a flash R to do essentially billion node graphs very fast on Carl's laptop. Okay, well, this is just an example of a 65 million node graph where we do this. So again, related a little bit to Catherine's controversial comment about don't cluster big graphs. So notice that this first level hierarchical stochastic block model is not trying to find all the fine structure. It's just trying to find whether or not there's coarse structure. And the answer is that yes, there were 16 coarse structure blocks, and in fact they clustered together, so it looks like 5 or 6 of them are very similar to one another, etc. So first of all, that's all well and good in practice. It works, but how does it work in theory? And the answer to that is we can prove the simple theorems based on the work in that HSBM paper if they're loosely enough connected, if those off-block probabilities are small enough, and you have the right kind of structure in there, you can find capital R hat converges to R, capital M hat converges to M. Everything works beautifully as long as you set it up to work beautifully. And then the great American sage Yogi Berra. So in practice, there are a lot of things that have to go on. We've heard a little bit about this before, but the actual motivating problem here, at least in 2013, was given to me that there were going to be 10 to the 6th neurons. Capital R will be 10 to the 4th because there's only 100-ish neurons per subgraph. And then there's structure within those subgraphs. So we most assuredly do not have enough data to do blind graph inference, right? But we have lots of covariates. We know some neurons are excitatory, inhibitory. We have to use the directions, but we know spatial location. So in order to actually make this work at the operating point of at least the neuroscience grand challenge, we can't do just pure graph inference. And that's all I have. And my time is up. I think it's a sane and interesting problem, and at least keeps me young. So graph inference, repeated motifs, and the cortical column conjecture.
We're running a bit over, and we have to break right now. So if it's okay with everyone, maybe we could have questions during the break. Let's thank all the speakers.
Thank you for your use. It worked okay.